All right, so I am applying for the AB calculus position. And so the concepts that I chose is definition of a derivative because it involves both derivatives and limits. So the students should be pretty familiar with the concept of rate of change up until this point. Usually slope and rate of change are used pretty interchangeably as they're working up through their math career with STAR and stuff like that. But usually average rate of change is the only slope that they're actually seeing. So if we were to give our kids a graph, choose 2 points and say, find the slope between these 2 points, or even find the rate of change between these 2 points. What your kids are gonna do is count the rise, count the run, and then calculate what that value is, rise over run. Okay, now you might have some kids that remember the formula y2 minus y1 over x2 minus x1. Okay, and that also is great if the kids tend to make that connection. But the slope that they're finding is actually the slope of a secant line. And so this draws a little bit on their geometry skills that when they're looking at secant lines on circles, these are typically going to be the lines that are crossing the circle at 2 different places. So we want to draw that connection in from geometry and then bring that to the idea of an instantaneous rate of change. So where a secant line is going to hit our graph at 2 points, we're going to ask the question of how can we do a slope through only 1 point? So we're going to call that an instantaneous rate of change. And rather than being over an interval from A to B, it's going to be at just 1 point. And that is what derivatives are used for. So let's draw our same picture over here. Okay, rather than me choosing 2 separate points and calculating the slope between them, I would just be picking 1 point. Maybe I choose this one. And then I would want to calculate exactly how steep the graph is at that point. So hopefully your kids would remember that means it's the slope of a tangent line. So if you draw your tangent line on there, it should lay perfectly next to your graph. And graphically speaking, that is what a derivative finds, is how steep the graph is at that point right there. So the question becomes, how do we turn the slope formula with 2 points into the slope going through only 1 point? So one more graph here before we get into an example. And I'm going to just keep that same kind of cubic shape here. Let's say that we have a point over here, A, and a point over here, B. So there's my point 1, there's my point 2. Here is the slope between them. Okay, what we want to do is define our points so that rather than having an A and a B, we have a little bit more cohesion with our letter or variable choice. So rather than calling it A, I'm going to call it X. And then I want this second point to be linked to my first point. So what I'm going to do instead is call this one X plus H, where H is going to be the horizontal distance measured from the first point to the second point. So if you had your kids right ordered pairs, this point right here would be X comma f of X. And this point over here would be X plus a little bit more, and then f of X plus a little bit more. So if you give those 2 ordered pairs, okay, to your kids and ask them to find the slope, they should come up with, remember our formula is y2 minus y1 over x2 minus x1. So it would be f of X plus H minus f of X. And then over x2 minus x1 would be X plus H minus X. Now, the problem is that that slope formula still involves a first and a second point. So in order to turn this into a single point, we're going to take this horizontal space between the points and we're going to do a limit where that space is going towards 0. And so essentially what's going to happen is that you're going to take this second point, and as your h shrinks down to 0, this point is going to get closer and closer and closer and closer and closer until eventually the points will be literally so close to each other that it equals what your derivative is at that x value. So you have your slope formula between 2 points, but then you're driving the second point closer and closer to your original using the limit as h approaches 0. So we're going to work 2 questions, and hopefully I don't go over 7 minutes, but we'll see. So first example I picked is x squared, typically because kids know what the graph looks like, and it's a little bit easier algebraically. So first I'm going to write my formula up here. F prime of x equals the limit as h approaches 0 of f of x plus h minus f of x, and then over x plus h minus x. So the first thing that I'm going to do is find what my f of x formula is from the problem. We want x squared. And then if I want f of x plus h, which is what we're going to have in our formula, that would be x plus h squared. So I'm going to take this formula, I'm going to plug these 2 expressions in where the names of those functions are up here. So we're going to have our limit in the front, h approach 0, of f of x plus h is x plus h squared, minus, and then f of x is x squared, all of that over x plus h minus x. First thing we're going to do is expand. If this is x plus h squared, that means that we can write it as a multiplication. Oops, sorry, my watch went off. We can write it as x plus h multiplied by itself. And I love teaching this concept because it brings back so much of like the old algebra. So we're going to expand this. X times x is going to go to an x squared. X times h and h times x are going to be grouped as a plus 2xh, because remember that xh and hx are essentially the same product. We have 2 of them. And then h times h, that's going to give me a plus h squared. We still have our limit in the front. We still have our minus x squared in back. And our denominator hasn't changed except for that I'm going to drop the parentheses so that I can look for anything that's going to cross out. Across the top, we should notice that we have an x squared and a negative x squared. Those can eliminate. Across the bottom, we have an x and a negative x, which leaves me with the formula, the limit as h approaches 0 of 2xh plus h squared over h. Now, at this point, we have a lot of different strategies to just algebraically evaluate limits. And so one of those is to factor cancel. So I notice on top that I have a GCF that I can pull a divide h out to the front. So I'm going to keep my limit in front. We're going to have out of the 2xh just a 2x, and from the plus h squared, now it'll just be a regular h. Then I notice now that the h is in the front, I can eliminate that with the h in the bottom so that I can plug in what h is approaching. Now, prior to this, if I had tried to plug in 0, the top would have been fine, but the issue comes in that if you plug a 0 into the denominator of your fraction, you have a divide by 0, that's undefined. So we now have the limit as h approaches 0 of the expression 2x plus h. And now that there's no longer an h in the denominator, we're going to perform our substitution. That's 2x plus 0, which gives us 2x. Okay, now kids also are going to learn the derivative rules. So the power rule, if you have f of x is x squared, the power rule would be that you would take this exponent up here, multiply it down to the front. So it would be a 2, and then your power squared would reduce by 1 to give you 2x to the 1, which is the same as the formula that we got with our limit or definition. Then typically what I would do, don't have a lot of time here, but I would find two values. So I picked -1 and 2, and I would have my kids find the slopes at both of those values. So we're practicing that notation. So f prime of -1, we plug our -1 in here. 2 times -1 gives me -2. And then I would have them sort of sketch the graph and see if that checks out. So y equals x squared is the parent function. Your kids should be familiar with that. And so if you go to -1, let's say that's here, and I were to choose that value, then think about if a slope of -2 would make sense for that tangent line. Okay, and hopefully it does because it's downhill. Okay, and it's not crazy steep, but it's a little bit steeper than like a perfectly flat diagonal. Okay, now let's try it. 2, f prime of 2. So we'd come over to our formula and plug in a 2 to that spot. 2 times 2 gives me 4. And then I would have them look at their parent graph that they sketched. We'll say 2 is here. Draw in that tangent line. And you should be able to see that my slope over here and my slope over here are matching the values that I'm getting using my definition. That a slope of here makes sense because it's a little bit steeper. It's also uphill versus a slope of -2 makes sense here because it's downhill. Okay, one more example. This one involves a little bit more kind of fun algebra. So we're going to do square root x. So we'll start off with our limit as h approaches 0 of f of x plus h minus f of x all over h. That's our definition for a derivative. My f of x value or equation is root x, which makes f of x plus x, this x plus h, the square root of x plus h. So now we're going to take those two formulas and we're going to plug them into these two spots in our limit definition. And actually, let me go back one step. This was x plus h minus x, but after the first example or two, usually this always crosses out. I'll just kind of no longer put it and only put an h on the bottom. But if you want to include it for a couple examples, it's fine. So we have the limit as h approaches 0 of f of x plus h is our longer square root minus our root x, and then all over just an h, because like we talked about, those x's are going to cancel each other out in the denominator. So at this point, I'll talk to my kids about, can I just cross these square roots out? Hopefully the answer is no. And so then it'll raise the question of, well, how can we get rid of them if they're both in square roots? And hopefully at least one kid remembers that you have what's called a conjugate. So you're going to take your root x plus h minus root x, and you're going to multiply by root x plus h plus root x. Okay, but we can't just multiply a conjugate on the top. So we're going to have to also multiply that same expression into the denominator. Okay, so we're going to keep the bottom the same. And usually kids are fine with that because they don't want to multiply these anyways. So we have our h and we have our x plus h under the square root plus root x. Okay, but the top of that we're going to multiply out. So root x plus h times another root x plus h is going to give us root x plus h squared. And then the squared and the square root will cross out. So that's basically just going to give us a regular x plus h. Multiply root x plus h times root x. Then multiply your negative root x times root x plus h. And then negative root x times root x is going to be a negative regular x. Let's extend that line a little bit further. So when you're asking the kids to kind of look for what can cross out, hopefully they're going to notice that these two terms actually are equivalent to each other because the order in multiplication doesn't matter. It's commutative. So if I have a positive and a negative of the same product, that can cross out. That leaves me with the limit as h approaches 0 of x plus h on top minus an x in the back over h and then my other conjugate that has survived on the bottom. Okay, from there, you should have your x and your negative x. Notice at this point, those can cross out. And then you notice you have an h on top and on bottom. Those can also cross out, which then kind of brings in that question of when you ask kids, like, well, what happens if everything crosses out on top? Is it 0? And hopefully they remember, no, it's not 0. It's going to still leave a placeholder up there of 1. So it'd be specifically 1 left over from the h, and then root x plus h plus root x. Now, if you remember from the last example, the reason we couldn't plug h in sooner is because an h plugged in to an h on the bottom gives you a divide by 0, versus now we do still have an h on the bottom, but it's in an addition. So basically that means that having a plus h in the bottom doesn't really matter as long as it's being added to something and not giving you that divide by 0. So we can take our 0, pop it in right there, which means that I have 1 over root x plus 0 plus root x. Well, remember that adding 0 to something doesn't really matter. So really, this is just root x plus root x, which means that on the bottom, really, I have 1 over 2 root x's. Okay, and then it says right here, we're going to check that that's right using our derivative rules. So if my f of x is the square root of x, that means that really that's x to the 1/2 power. And so remember what we said about taking derivatives. For f prime of x, I'm going to multiply that 1/2 down to the front. And then I'm going to decrease that power by 1. So if it's a half, and I take away 1, that gives me negative a half, which then brings back all the rules that they did in Algebra 2, that if you have a negative exponent, that means that that term really belongs on the bottom with a 2 in the denominator. And then remember that a 1/2 power is the same as a square root, which means that really we got the exact same answer using our limit definition as we would have gotten using our rules definition. Then just real quick for the slope, this should be a positive. Let's do 1 and 4 so that we're picking easy numbers to plug into our square root. So if I did f prime of 1, that would be 1 over 2 root 1. Square root of 1 is 1, so that'd be 1 over 2 times 1, which is a half. And then let's plug in 4 as well, so that when we're checking our graph, we have 2 points to look at. So it's 1 over 2 root x. In this case, that's a 4. Well, the square root of 4 is 2. 1 over 2 times 2 is a 4th. And so then what I would do is have your kids go through and look at the square root graph and see if that makes sense. Sort of connecting that graphical concept with the algebra. So y equals square root x. Hopefully the kids know what it is because it's one of the parent functions. 1 would be here. And we're saying that our slope is a half. And if I come out to 4, so we'll do 2, 3, 4 is here. My slope is a 4th. And so then you can have the kids kind of look at it and say, well, how do I know that a half would go to a 4th? Well, if this is a little bit steeper and then it got flatter, then you can tell that that slope went from something bigger to something a little bit smaller. Okay, also, if you were originally, this was a -1, if you change this to a -1, then you end up with the problem of, oh, I can't take the square root of a negative. So the derivative at -1 is going to end up being undefined, that we can't find that, right? Okay, but then think about your square root graph. Does it even reach back here at -1? And the answer is no, because it's not in the domain. So anyways, I love teaching that just because of all the connections, but that's the end of my video and I hope that you pick me. Thanks.